In week 1, we first saw what is vector addition and what are how to do scalar multiplication, right? So suppose you have some vector v from Rn, and you do, for let us say for example R2. So what does alpha v does? So whatever is your v, your alpha v will be on the same line as that of your v, right? Whatever is your alpha will be on the same line as that of v, right? So that is scalar multiplication. And for vector addition, you know that it follows parallelogram law in R2, right? So for matrices, if you have an m by n matrix, you know that m represents the number of rows and n represents the number of columns, and this is the size of the matrix. You know that for matrices of same order, you can do addition, you can do scalar multiplication, and for multiplication, what is the rule you need for the order of the matrices? Suppose you have a B cross K matrix, or M cross N M cross N, and let us say B is your N cross P. Can you tell what is the size of the matrix C, which is A into B? What should be the size for C?
M into P.
Cross.
M into, right? Fine. Okay. So you know.
Simply, ma'am, Madhya Pradesh shortcut.
Sorry, what?
Simply, ma'am, Madhya Pradesh short form.
Please don't give unnecessary things here.
Ma'am, please continue.
Yeah. So if you have a matrix A, which is an m by n matrix, what should be the size of the transpose of A?
N by M.
N by m, right? So if you have the entries of A as Aij, then A transpose should have the ijth entry of A transpose, it should be Aji, right? So that is the transpose, right? And for matrices, what are the types we know? We know rectangular matrices, so the general M cross N matrices, and then we know N by N matrices, and then we know diagonal matrices. It means what? Aii, Aij is equal to 0 for all I not equal to j. So such matrices are called diagonal matrices. And for scalar matrices, you know that Aii should be the same alpha, and Aij should be 0 for all I not equal to j. These are scalar matrices. Okay, and 0 or null matrix, you know that all the entries should be 0. For diagonal and scalar, they are square. This can be any rectangular matrix. And identity matrix are special type of scalar matrices where all the diagonal entries are exactly equal to 1, right? And triangular matrix, it depends on upper or lower triangular. So you can have either upper triangular or lower triangular, right? So for upper triangular, you have Aij, where J is, I'll write first. So I strictly greater than J, this part is 0 for you, right? This part is 0 for you. So if you have, for example, A11, A12, so this 1-2 part, A21 part, that is where 2 is greater than 1. So this part is 0 for you, right? And for lower triangular, just the opposite of that. So you have Aij equal to 0 for I strictly less than j. Okay. So this is lower triangular and this is upper triangular. Okay. Fine.
Ma'am.
Yes.
So, ma'am, a scalar matrix can also have all the elements as 0 also, right? Which is the
Yes,
null.
no, scalar is not a null matrix. Scalar is a diagonal matrix, right?
Okay. Okay.
If we multiplied with the scalar 0, then it's null matrix.
Null is a special case of scalar, but scalar matrix does not mean that it is null. Okay, so it is possible that alpha is 0. That's all.
Okay, so it is possible, right, ma'am? Alpha is 0.
Yeah. That is possible. Yeah.
Okay.
Can we say that scalar is a special case of diagonal matrix?
Yes, of course. Okay, they are subsets, right? So you see that you have all m by n, and then you have all n by n sitting inside, and here you have all the diagonals sitting inside. Right, and then you have all the scalars, and then here you have all the identity matrix. Right, so if you have
What
an
is this
identity
for?
matrix,
What is this?
if a scalar matrix is diagonal, a diagonal matrix is an n by n matrix. So the order goes in this way. Okay, fine.
Yes, ma'am.
Ma'am,
Yeah,
no, sorry to ask, ma'am, till which week we have session?
week 1 to 4. Okay, so let's look at system of linear equation. System of linear equation. First given a system here, the first thing is that we do a matrix representation. Here, m represents m represents what and n represents what? Can you tell me quickly? M represents the number of
columns.
Rows.
equations in the system.
Yes, ma'am. System of linear equation. Yeah.
Yeah, and n represents the number of unknowns.
Variables.
Yeah, variables or unknowns.
Yeah.
So you see that for this system, you have an m cross n matrix representation, right? And the solution is a vector in Rn, right? So quickly tell me, the first picture depicts how many equations?
No solution.
No solution, and there are two equation. Yeah.
Yeah, you have two equations with two variables, right? This axis represents the variables, right? Two equations with two variables, and this is a scenario where you have no solution, right? Okay, what about this? Here also you have all these are representing actually two equations and two variables. So here you have a unique solution. And what about this case?
Infinitely many solutions.
Infinitely many solution.
Infinitely.
Hello, ma'am. Can you tell me the syllabus of Endterm examination
Everything, week 1 to week 12.
and what is the weightage?
There is not any precise weightage, but approximately 50 for week 1 to 8 and approximately 50 for the remaining weeks.
Okay. 9 to 12.
Yes.
Ma'am.
Okay. Thanks, ma'am.
Yeah, please don't interrupt the session. Whatever doubts you have, please ask at the end of the session. Okay, fine.
Okay. Sorry, ma'am.
Match the system of linear equations in column A with their number of solutions in column B and their geometric representation in column C. So here, look at this equation. X plus y is equal to 3 and x minus y is equal to minus 3. What is the solution for this equation?
Unique.
Yeah, it has a unique solution because what is the matrix representation you have? 1, 1, 1, minus 1. What is the
Yeah.
determinant of this matrix?
-2.
-2.
So it is non-zero, so you can immediately say that it has a unique solution, right? And you can see that this
Yes.
is the one which represents a unique solution. And here you see that, so you know that what is the general equation of a plane? So it is ax plus by plus cz is equal to d, right? Now you see that you have two planes and you also notice that the coefficients are same except d. So it means what? They are parallel planes.
Parallel.
Right? These are parallel planes. So if there are parallel planes, will they intersect?
No, this means no solution.
Yes. So it has no solution. So it means
But how we concluded parallel planes to such like equations like x plus y. Okay.
so the coefficients are same for both, except the d part. The coefficients of x, y, z are same, right? So that's why they are parallel. Okay,
Yes, ma'am.
fine. And the last one, you see that you have, when substitute z is equal to 0, the equation reduces to x plus y is equal to 1, right? It means you have how many solutions?
Infinitely many.
Infinitely many solutions, right? So you see that this will match with this, and here the picture is this. Okay, so you have the z is equal to 0 plane and the other plane intersecting with it. Okay, fine. So this is how you can compare the
Could
solution.
you please repeat the third one, the 3D one?
Exactly.
So the third one, you see that here z is equal to 0 and x plus y plus z is equal to 1. So first we are substituting z is equal to 0 here, and then you see that x plus y is equal to 1. So now one of the variable is, you see that is, you have to take some arbitrary values for that. Suppose for example, you take y is equal to t, or in fact you can even keep y is equal to 1 minus x itself, so that you can write the set of solutions. So you see that what are the solution for this equation? Set of all x comma 1 minus x comma 0. So you see that it satisfies both the equations. Z is equal to 0 and the sum of all the terms is equal to 1, right? So this is the solution set, right? So if this is the solution set, you know that this is representing a plane, right? So so this is actually representing infinitely many points. Okay, so you can see that this is the infinitely many solution part, and obviously you see that z is equal to 0 is along this x and y axis. You can see that from that you can say that this is z is equal to 0, and the other plane you can just have to guess, because we don't have any specific measure here, but z is equal to 0 at least is very clear here, right? So you can match the solution here. Okay, fine.
Ma'am, x comma 1 minus x comma 0 is a line, right?
Yeah, sorry, yeah, because only you have one variable to, sorry,
Yes,
one
ma'am.
vector to span this set. Yes. So can anyone tell what is the spanning vector for this set? How to find the spanning vector for this? By the way, this is not a subspace, so we cannot do the spanning, right? Yeah, fine. Yeah.
Yes, ma'am.
Yeah,
Oh,
it's not a source
okay,
vector.
okay. Yeah, fine.
Ma'am,
Okay. Yeah.
for this diagram, can you write which is x-axis for
Sorry, what?
that? For this diagram, can you write x-axis, y-axis? It will be clear.
So this is your z here. So one of this should be x and the other should be y here. So your z is completely 0. Okay.
That means x, right?
Okay.
Ma'am,
Yeah.
we can consider this as an affine space, x1 minus x0.
Why you want to consider it as okay? So if you want to add one vector, yes, you can consider it as an affine space. Yes. Okay.
Ma'am, I'm really
Also,
worried
ma'am,
about
because of this one,
Sorry, what?
also because of this one, also it will act as an affine subspace, right?
Yes. Because of the one, it is an affine space. Yes.
Okay, thank you.
Yeah. Okay. So now, looking at the next topic, which is determinants. You know that someone should mute. Everyone, please mute. Yeah. Okay, so you know that the determinant of a 1 cross 1 matrix is exactly the number itself, and for 2 cross 2 it is AD minus BC, and for 3 cross 3 you know that you have a formula like this, and this is not the only formula. You know that the formula takes several forms based on the minor and cofactor formula, but this is the typical one which many of you use, right? Okay, what is the determinant of an identity matrix?
One.
one.
What is the determinant of A transpose in terms of determinant of A?
A.
Equal to
Determinant of A.
It's just the determinant of A. What is the determinant of A into B?
Determinant of A into
Determinant of
determinant.
A.
Okay, so is it applicable for any finite product? So you have determinant of A1, A2, AN, then also this is possible, right? Determinant of A1 into determinant of A2 into etc. determinant of an. Okay, fine.
Determinant of a power and determinant of a power.
It's not power, it's just sub here you have just suffix. So a1, a2 you have.
This is order dependent.
See, these are numbers. So order does not matter. These are just real numbers.
No, for the determinant of AB, so we cannot write like determinant of B into A for that.
See, determinant is just a number. That's what I'm saying. Determinant of BA is determinant of B into determinant of A. Now, these are real numbers, right? So, the order does not matter. Because of this only, determinant of AB and determinant of BA are same.
Okay.
Okay. And what is the determinant of inverse of a matrix? So, whenever we are inverse, already we know that determinant of A is non-zero. So, it is 1 by
determinant of
Joint of
So suppose you have some triangular matrix. What is the determinant?
Product
of the
diagonal
diagonal entries.
Okay, determinant of a matrix with 0 row or column?
0.
Right? Okay. So what are row operations? So either you can switch rows or you can multiply a row by a non-zero number. Remember, the non-zero is important. Non-zero number, or replace a row by a multiple of another row added to itself. Okay. So what are the properties of determinant based on the different row operations? So whenever you are switching rows, the determinant changes. Okay. And whenever you are multiplying by a non-zero scalar, then what happens? The determinant gets multiplied by that scalar. Okay. And when you are replacing a row by a multiple of another row added to itself, the determinant does not change at all. Okay. So these are some very important properties. So here you see that because of these properties, you have the following result. So if A is an n by n matrix and B is equal to alpha times of A, then determinant of B is alpha power n times of determinant of A. Right? So here this n is the order of the matrix A. Right? So now based on this, can you tell me the answer for this? If determinant of minus 2A is k times of determinant of A, what should be the value of k? So given
-8.
Yeah, so here n is equal to 3, so your k should be minus 2 power 3, which is minus 8. Right? Okay. Now, yeah.
Are order and size the same?
Order and what?
Order and size of a matrix the same?
Order and size of the matrix, order of the matrix, same only.
Ma'am, for this last property, where we are multiplying a scalar to the determinant and it becomes k to the power of order. So for a like if n equal to an even order matrix, if I say, it will always be a non-zero determinants, non-zero value, non-zero.
We
Sorry,
don't know about it.
Non-negative.
Yes, yes. This is non-negative, but you don't know about the determinant of A. Okay, fine.
Ma'am, a small interruption. Could you just mute everyone, ma'am? Unnecessarily, they're unmuting. It's causing a disturbance.
Okay.
Ma'am, please unmute yourself.
Not on mute. Why Nandakumar?
Yeah.
Nandakumar, I'm not able to mute him alone. Why is that so?
Pardon me?
Please mute yourself.
I didn't follow.
Nandakumar,
Yeah.
can you please mute?
Yeah, just joined now. And I am the oldest student of the university.
That's fine, but please mute. Yeah.
Yeah.
Ma'am, let's go.
Yes, I'll continue. Even I tried mute all, but still it's not working. Okay, fine. So the three different types of elementary row operations which are performed are this, and equation 1, 2, 3 are here. So you see that, okay, so this problem I guess I have already discussed. So maybe I'll ask something different. So let us say I'm having some matrix A, okay. So the determinant of A is, let us say, some 10. Determinant of A is 10. Okay. So I'm going to multiply row 1 with -1. Okay. Multiply row 1 with -1. So -1 times of R1. And I am multiplying row 2, or let's say column 2. Column 2, I'm going to multiply with 2. And then I'm going to replace row 3, exchange row 3 with row 2. So what is the resulting matrix, I'm calling it as B. So what is the determinant of B? Can you tell?
10. The same.
It's just 10?
10 or 20?
Yes, ma'am.
20, ma'am.
See,
Not
first
20.
10 becomes -10, the first operation. And then -10 becomes
20. Minus
minus
20.
20. And then -20 again becomes
20.
20. Right? So the determinant is 20. So you see how the different row operations can affect the determinant of a matrix, right? So this is a similar problem. I have done this already in the session, in the class session. So I thought I can do a different one here. Okay. So maybe you can try this yourself. Okay. Let A be a square matrix of order 3 and B be a matrix that is obtained by adding 2 times the first row of A to the third row of A. Okay, and adding -1 times of second row of A to the first row of A. So what do we know about this row operation? That is the multiplication of one row added to another row. So does this affect the determinant at all?
No.
No.
It does not affect. So that kind of an operation is done twice here. So you know that the determinant of B is going to be same as determinant of A. So in that case, what should be the determinant of this matrix? Can you tell?
27. 20.
3A square
15.
-5 cube.
27.
3 cube
27
times
into 5.
determinant of A whole square 1 by determinant of A. So what should be the answer?
27.
5 into 27.
-27.
Into,
Determinant of A.
right?
-5, yeah.
So it is actually just only -5 only, not minus, because we are squaring and then cancelling out, right? Or, oh, here also minus is there. So -1, yeah. Okay, so this is the answer.
-135.
Yeah, yeah.
Okay, the negative one is adjusted at the end.
Negative? Sorry, what's your question?
There is a second operation adding -1 times the second row of A to the first row.
Yes, that operation is also exactly similar to the first operation, right? It is of the third type here, right? So for the third type, we know that this does not affect the determinant. Yeah?
Yeah, okay.
Okay, so this is the formula for determinant in terms of minus and cofactors. Okay, this is something you need to remember. Okay, so moving to week 2. So solutions to system of linear equations. You know that if a system Ax is equal to B has a solution, then we say that the system is consistent, and if there is no solution, then we say the system is inconsistent. So for in the consistent case, you know that there are two possibilities. Either it can be unique or it can have infinitely many solutions. Right? So the very simplest case is when you have an invertible matrix. So it means we should know what is the inverse of a matrix. What is the inverse of a 2 cross 2 matrix? It is very simple. 1 by determinant of A into the adjugate of A. So here you see that in this case it is very simple. You interchange this part A and D, and then you change the sign for this part. So you get the inverse.
Ma'am, I want to ask one thing.
Yeah.
In the scenario earlier, unique solution and no infinitely many solutions, that is zero now or non-zero?
Sorry, what infinitely many solution? What?
Determinant is not equal to zero now.
Infinitely many solution, determinant is equal to 0. So only when unique solution you have determinant is non-zero. Here you have determinant equal to 0. For square matrix case, you have this property. Okay,
Or
so
no solution.
determinant of E equal to 0 can either have infinitely many solution or no solution. Both are possible when determinant of A is 0.
Yeah, exactly. I was asking.
Okay, only when this you have determinant of A non-zero, then only you can guarantee that it has a unique solution. So determinant of A is equal to 0 has two possibilities: infinitely many and no solution. Both are possible. This is for non-homogeneous. Whatever I am saying is for non-homogeneous. But for homogeneous case, what happens?
Trivial solution.
X is equal to B, this is the case, so B non-zero. But when you are using a homogeneous case, that is A is equal to 0.
Yes, zero.
Yeah, so determinant of A non-zero says that you have a unique solution, and determinant of A equal to 0 says that you have infinitely many solutions. Only these two are the possibilities here. No solution scenario is not here at all. Okay? Fine.
Ma'am?
Yes.
We can get this inverse by augmenting I to A also.
By applying what?
We can get the inverse of a matrix by augmenting
Yes.
identity matrix also.
Yes, yes. You perform the row elimination and you get it. Yes.
Ma'am, this one A into A inverse is equal to A inverse into A, right?
Yes, yes. There is a mistake here. A inverse into. Yes. Thanks for pointing out. Yeah.
Ma'am,
Yeah.
can I ask you a bit off-topic question here?
Yes.
Like from the later weeks. Ma'am, how to find out whether two matrices are similar or not?
Please
Because like
hold on.
we have to find out.
Hold on. You have a session on Sunday for week 5 to 8. Please ask them. Okay.
Okay, ma'am. Sorry, ma'am.
So solution of a system of linear equations with an invertible coefficient matrix. So here you have a system Ax is equal to B, where A is an invertible matrix. Then solution of the system of linear equation can be obtained as follows. So Ax is equal to B you have here. Okay. So you know that to obtain the solution when A is invertible, you simply have to find A inverse B. So A inverse B gives you the solution. Nothing more than that. Yeah. So applying that property here. So here, actually not that property, but yeah. So here you see that you have a system of linear equation. So it is given that this system has a unique solution. So what is the criteria for A to have a unique solution? I already told you just before.
Determinant is not equal to 0.
So the matrix A is 1, -1, 3 and k. So what should be the, so if determinant of A is not equal to 0, what is the determinant here? K?
+3.
Yeah.
1 - 3.
This is non-zero. This means that k is not equal to -3. Right?
1 minus 3.
Sorry, what?
Matrix, the first row.
Oh, sorry. Yeah, it's minus 3 here. Yeah. 1 minus 3, 3 and k, and so you have k plus 9. So k is not equal to minus
10
9.
not equal to 9.
Okay, fine. All right. Solutions of a homogeneous system of linear equation ax is equal to 0. This system is always, can you tell? It is always?
Consistent.
Yeah, it is always consistent. And what is a solution for this system?
0
What?
is always solution.
Yeah, 0 is always a solution, right? And when
Then
a
consistency only denoted as ax is equal to 0.
it's not a denotion for consistency. Consistent means existence of solution.
So there is always a solution for homogeneous system.
Yes. Okay. So if A is a square matrix and determinant is non-zero for homogeneous system, then the system has how many solutions?
Unique solution.
Unique solution.
Unique solution.
What about when determinant of A is 0?
Infinitely many.
Infinitely many solutions. Okay. Now the same when A is rectangular. If A is an m by n matrix, first of all, m represents the number of equations.
Equation.
N represents the number of variables, right? Now, if m is greater than n, then what should be the maximum value of rank of A?
N.
N, right? Now, if m is greater than n and rank of A is equal to n, so the system Ax is equal to 0. How many solutions does this have?
Infinitely many.
Hold on, you have a full
No,
rank
then
here.
Unique solution.
unique solution.
Unique
Right?
solution.
Whenever you have doubt, just look back at rank nullity. So you have a full rank matrix, so nullity should be 0, right?
Yeah,
So it
ma'am. So
means you have
basically, no independent variables, right?
yeah. Okay. Now you see that if m is greater than n and rank of A is strictly less than n, then the system has
Infinitely many.
Infinitely many solutions.
Now what happens when you have m is less than n? Then irrespective of what
Infinitely many.
the system will always have infinitely many solutions.
Ma'am, can you repeat
I
this
have a
question?
doubt with the case 1.
Yeah.
Ma'am, here it is given for a homogeneous ax equal to 0, the system is always consistent and 0 is always the solution. For non-homogeneous, 0 is a solution means it will always have one or unique solution basically.
I have not talked about non-homogeneous yet. We will come to that part quickly. Okay. This is only
Ax
about
equal to b, ax equal to b, then it was.
Yes, that's we are going to see it after a few slides. Okay. Okay. So moving on to Gauss elimination method. So
Ma'am, ma'am, m less than n means there are more variables on equations, right? So that's why it is
yes.
That's why it is infinitely many solutions.
Yes.
Okay, ma'am.
You have more free variables here. That's why. Yeah. Okay. So
Yes, thank you.
when do we go to Gauss elimination? So either you have Ax is equal to 0 and you have A is a rectangular matrix, or if you have the determinant of A is 0, then you can go to Gauss elimination, or you have Ax equal to B, then also you can use Gauss elimination if A is not invertible. Okay. And for rectangular matrices, of course, you can use Gauss elimination. So only when inverse exists, you can apply this. In all other scenarios, you have to rely on Gauss elimination method. Right? So for Gauss elimination method, what is the first thing we have to do? We have to first convert the matrix in the REF form, right? So what is that? So first thing, the leading entry in each row should be 1. What is leading entry? The non-zero entry, right? The first non-zero element in each row, we should make it 1, right? And the next thing is that each leading entry in a column is in a column to the right of the leading entry in the previous row.
Yeah.
Okay. So here you see that. So for example, here you see that this is a column to the right of the previous leading entry, and same way here. Okay. And then rows with all 0 elements, if any. If there are any 0 elements, so for example, you have 1, 0, 0, 1, then 0, 0 should be at the end. Okay.
Yeah.
So the 0 column comes at the end. So for a non-zero row, the leading entry is the only non-zero entry in its column. Okay, fine. So here you see the last property. Is it satisfied here? The
Yeah.
leading entry is the only non-zero entry in its column. So for example, here this is the leading entry. Is it the only leading entry in this column?
Yeah.
Yes.
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 You have another non-zero entry here. How can you say yes?
But that is not the leading.
Okay, so in this column, there is another non-zero entry. So this is not in REF form, RREF form. So this is not RREF. Okay,
This is in the REF form, madam.
this is in REF form, but not RREF, because this
Yes,
property is not satisfied. So here you see these are the leading entries. Now look at the columns containing the leading entries. Apart from the leading entry, all other zeros in those columns are 0. So this means that this is an RREF. Okay, you understand the difference here, right? Okay. Now, once you know how to find, convert a matrix into REF form, how to find the solution? So, okay, I have not given how to find, but yeah, how to find the solution. So, suppose you have a matrix AX is equal to B, then what you do? You take the augmented matrix AB and make it in REF form or RREF form, whichever is easier, you can do that. So you convert in REF or REF form. Let's call the equation you obtain as Rx is equal to C. So now this is a simplified system which has the same solution as Ax equal to B. So you solve this solution system and you will get the solution for Ax is equal to B. All right. Okay.
Ma'am.
Yes.
Ma'am, Gaussian elimination we can use for a square matrix also, right?
Yes.
Any matrix. Okay.
Yeah. Gaussian elimination is applicable for all type of equations, system of linear equations. Yes.
Okay, thank you.
Okay. So let us say you are having some some system Ax equal to B where A is already in the reduced row echelon form. Okay. So also assume that in the reduced, whenever you have a 0 row and the corresponding entry Bi should also be 0. Okay. So that scenario we are assuming. Okay, so whenever you have a non-zero, if all the rows are non-zero, then all the entries of B should be non-zero. And if there is a 0 row, then the corresponding Bi should be 0. So this is the condition we are assuming. That is, we are eliminating the case of no solution. So now here you see that what are the remaining cases. So if A is square and invertible, so for example, it will be the RREF form is of this type, right? And if A is an m by n matrix where m is greater than n and rank of A is equal to n, both are full rank cases, right? So the rank is full in both the cases. In this case, the RREF form is of this type. Okay. So in these two scenarios, you have unique solutions. Okay. So in both the cases, you have full rank and you have unique solutions. Okay. Now, what about infinitely many solution case? For infinitely many solution, what are the possible cases? So if m is greater than n, then what happens when rank is less than n? You have infinitely many solutions. Also, when m is less than n, what happens? You have infinitely many solutions. Assuming this condition. Remember, here we have this condition under assumption. Okay, so without this condition, we have more cases. But when we are restricting to this case, only these are the remaining scenarios. Okay, fine.
What is the condition, ma'am, that you're talking about?
So whenever there is a 0 row in the reduced row echelon form, we are assuming that the corresponding entry, Bi entry is also 0. Okay?
Okay.
So if it is not zero, then it will be then the system will have no solutions,
Exactly.
right?
Yes, then you don't have to check these at all. Directly you can stop here, saying that the system has no solution.
Okay.
Okay, fine. Okay. So next we will see what are dependent and independent variables. Let Ax is equal to B be a system of linear equations where A is in reduced row echelon form. Okay. Now assume that for each zero row of A, the same assumption which we had, the corresponding entry of B is also zero. So it means we are assuming the system has a solution. Okay. So now if the ith column has a leading entry for some row, we call xi a dependent variable. Okay. So for example, for this matrix, let us say the first column, does it have a leading entry?
Yeah.
So now you can say that x1 is dependent. What about the second one? Does this have any leading entry?
No, ma'am.
So it means
That
x2
is
is
independent.
independent. And what about the third one? It has a leading entry, so you have a dependent variable. Is that clear? Yeah.
And if m is equal to n, then also we have to check rank, right?
Can you please repeat your question?
There is a case that is not there. If m is equal to n, then checking rank is enough.
So you are
Clear?
talking about the square matrix case. So you are asking, you want any specific conditions? What is your question? Sorry.
I'm saying if m is equal to n, then checking the rank is enough for consistency.
Yeah, that is enough. Actually, finding determinant itself is enough. When you have m is equal to n, square matrix case, just find the determinant, determine non-zero, you know the solution exists, right? And
Okay.
it is unique also. And finding the rank is even better, right? Yeah. Consider a system here. So what is the matrix first of all here?
0, 1, 0, 0.
0, 1, 0, 0, 0, 0,
0, 1, 0.
1, 0. So you see, this is a column which contains a leading entry, and this is a column which contains leading entry. So x2 and x3 are your dependent variables, right? And x1 and x4 are independent variables. Okay, fine.
Can you repeat the infinite and unique solution question?
Which one? This one?
Yeah, this one. Can you give me
See,
a quick summary?
uh, see here I have not said anything, nothing much. So when you have m is greater than n, there are two possibilities: either the rank is equal to n or the rank is less than n. These are the two possible scenarios. When you have rank equal to n, you have unique solution, remember, under this assumption. Okay, and if rank is strictly less than n, then you have infinitely many solutions. So this is one example where you have rank is strictly less than n. So for example, for this matrix, so what is the size of this matrix? This is a 3 cross 2 matrix, right? So here you will have, for example, if you are considering a x1 x2 is equal to, let us say, 3. We are assuming that whenever there is a zero row, the corresponding entries of BA is also 0. So under this assumption, what is the condition you are getting? You are getting x1 is equal to 3. So what about x2?
0.
X2 can take any value. X2 is your free variable here, right? So 3 comma t, t in R. So this is your solution set for this Ax is equal to B. So you have infinitely many solutions, right? So the similar scenario comes here also. So if you take x1, x2 and some other numbers, x1, x2, x3, and take some other vector here, you will end up with something like this. Fine? All right?
Ma'am, could you once explain the assumption above? I have missed it, ma'am. The node section over here. Yes.
See, here this is the RREF form, and here we have 0 rows. We are assuming that this is your B. So the second row, row 2 and row 3 are 0. So I am assuming that B2 and B3 are 0. Is it clear?
Yeah.
So whenever you have an RI 0, then you are assuming your BI is 0. This is the assumption. Okay?
Okay. Okay, ma'am. If it is not 0, then no solution will be the case.
Yes.
Got it. Yeah. Please move on, ma'am.
Yeah. Okay. So, this is the step which I have explained in short here. Where is that? Yeah. So whenever you have a system AX is equal to B, you consider the augmented matrix, convert into the reduced row echelon form, call that matrix as RC and the equation as Rx is equal to C. So the solution of this reduced system is same as the solution of AX is equal to B. Right? Okay.
Yes, ma'am.
Okay. So now we can move on to week 3. So far I have quickly covered week 1 and week 2. I hope it is fine. So in week 3 we will see what are vector spaces. So in vector space, the first thing is always you need to check closed under addition and closed under scalar multiplication. This is the first step you always have to do, and then you have the remaining 8 axioms, and you know that the first 4 axioms are based on vector addition, and then next 2 are based on scalar multiplication, and the last 2 are combinations of addition and scalar multiplication. Okay, so these are the axioms you need to check. Okay, and you know that these are some familiar examples for vector spaces, right? And always a subspace is a vector space. Remember that any subspace can also be considered as a vector space itself. Okay, fine. And some properties, you know, that cancellation law applies, 0 vector is unique, the inverse is unique. Okay, fine. Now looking at subspaces of vector spaces, for subspaces there are two things. First of all, you take any non-empty subset, okay, of the whole vector space, and you need to check two things. See whether it is closed under addition, and see if it is closed under scalar multiplication. If these two conditions are there, then you know that it is a subspace, right? So for example, for R2, what are all the possible subspaces? For R2, what are all the possible subspaces?
The line.
The x-axis, the y-axis.
R2, and then you have any line passing through origin, right?
Yes, ma'am.
And then you have,
Ma'am, it can be just any line, right? Like,
yes, any line which passes through the origin. Okay, so passing through the origin is important. And for R3, you have one additional case. You have any plane passing through origin. So the whole R3 and any plane passing through origin. And then
why does it have to pass? Oh, okay, I got it.
Yeah.
Ma'am,
Any,
because
yeah.
it's a subspace, right? That's why, right?
Yes, yes.
Okay.
And then you have the zero space. So for any vector space, the whole space and the zero space are the trivial subspaces. Okay. And for R2 and R3, these are the only possible subspaces. Okay. Any subspace will take any one of this form for R2 and R3. Okay. Fine. Okay. So here is the example for an subspace of R2. So this is a line passing through origin. So you know that it is a subspace, right? And in the case of matrices, you have some subspaces like this. Okay, so for example, let me ask a very simple question. Let us say you have set of all maybe A, B, C, D, such that determinant of, let's say A, okay, such that determinant of A is equal to 0. Now, What can you say about this? Is this a subspace? Is this a subspace?
Yes, ma'am.
Okay.
Yes, ma'am.
Are you sure that this is a subspace?
One dimension always there, madam. It is not two dimension, it is one dimension.
Okay, you are saying this is a subspace. Now tell me, does this matrix belong to you? What is
Yes,
it?
ma'am.
Okay.
Yes.
What about this matrix?
Yes.
What
Yes,
about their sum?
one dimension.
What about their sum?
This also, madam.
No, ma'am.
The determinant is 1, right?
Yeah, determinant is
Okay.
So it is not in you. So it means this is not a subspace of is the M2
W.
by 2 of R. Right? So this is not a
Ma'am,
subspace.
excuse me. This the U's are we have written the first and the second is not a subspace of the U na.
Not, these are elements of U, right? Because the determinant is 0 for this, the determinant is 0 for this. So these are elements of U.
Yeah,
Okay.
elements are called the subspaces for U na.
No, no. We are having a set and we are checking whether this set is a subspace. Okay, this as a subset of M2 by 2 of R, is this a subspace? We are checking. So for that, we need to take two elements here and see is it closed under addition.
But it means if for a matrix the determinant is 0, then it is not a subspace.
See, this set, the set of all matrices for which determinant is 0, that set is not a subspace.
Oh,
Okay, fine.
fine.
So if you take the
Set of all ma'am, excuse me. Set of all subspaces that don't have determinant is equal to 0 is not a subspace of this na.
set of all matrices which don't have determinant.
Determinant is 0.
Determinant is not zero is a subspace.
That also
Determinant of not equal to 0 is not a subspace of this na.
subspace of it means what? I first of all don't understand your question at all.
Ma'am, my query is there is a written part where U is equal to ABCD, right? So
Yes.
whenever we just computed at A1 with 1 0 0 0 and U, we are just checking two components of it. If it is not, it is adding under adding, but we are not getting the same thing as U. So as a conclusion, these are not subspaces of each other, na?
I guess you don't understand the concept here. So these are not like subspaces. We have taken what is the property of can you tell what is the property of closed under vector addition means? What is meant by closed under vector addition?
That two vectors when combined together and forming the same thing that we want to compute if comparison.
It's not forming the same thing, it belongs to the same set, right? So here this is a vector and this is a vector, and I am seeing whether this some of these vectors belong to the set and it does not belong to the set, and hence this U is not a subspace. Okay, so here A1 and
Yes.
A2 are okay, fine. I guess it's time to move on. This is a very
Yes, ma'am. Yes, ma'am.
yeah. Okay. So also same way, if you take all the invertible matrices also, that is also not a subspace only. Okay. So again, you can generate examples. So for example, you take this matrix 1 1 0 0 and then you take the negative of it. What happens? The sum is a matrix.
Zero.
Yeah,
Zero is not equal.
it's not invertible, right? So this is again not a subspace. Okay, fine.
Ma'am, so in the cases where matrices or where vector spaces of matrices are involved, we have to check the things using examples only, right? Like we can't really write equations for this,
Yes,
isn't it?
yes.
Okay.
Fine. Okay, so sometimes you have like conditions. For example, a plus b is equal to 0, c plus b is equal to 0. There you have to right? B in terms of A and D in terms of C. Yeah, that is also there. Okay.
Okay, ma'am. Thank
It depends on the condition given on the matrix.
Ma'am,
This is week 3, ma'am.
Yes.
second point I don't understood. Second, why 2 cross 2 is not a subspace matrix? Yes. Second, third example, third.
See, here your A1 is this and A2 is this. These two are invertible matrices, but A1 plus A2 is zero matrix and it's non-invertible. So this set is not closed under addition. So it's not a subspace, right?
Okay, madam.
All right. So the next topic here is what are linear combinations. So let V be a vector space and V1, V2, Vn be elements of a vector space V. Now what is a linear combination? So you take all the scalar multiples of each of the vector and add them up. So all possible such combinations are called linear combinations. So it is, okay, first of all, what is linear combination? You take some scalars, multiply with each vector and add them up. That is a linear combination. So this is true for any scalar. Okay, so you can have infinitely many linear combinations for a given set of vectors. Even if you have one single vector, then in that case linear combination is nothing but, can you tell, in case of one vector, what is linear combination?
1.
No. What is
Ma'am,
linear? Yeah.
A into V basically. Like
It
if
is, yeah, it
yeah,
simply reduces to scalar multiplication.
yes,
Right?
yeah, yes,
So when
yes.
only when you have one vector, then linear combination is all possible scalar multiplication. Okay, so when you have more than one vector, then you do the multiplication for each vector and then add them up. That is linear combination. Okay, fine. Now,
Yes, ma'am.
yeah. Now, can you all try this one quickly? Everyone, please try this quickly. So you have a vector v 3, 4, which you can write as AV1 plus BV2. How do you find A and B?
A plus B is equal to
So A plus B.
A plus B equal to 3.
Yeah.
B minus A equal to 4.
A minus A plus B.
Right.
B minus
First
A,
of
whatever.
all, how do you know that this system has a solution?
Because there are equal number of variables and equations like that.
No. What is the matrix? 1, 1, minus 1, 1. And the determinant is non-zero.
Yeah,
So
not zero. Yeah.
so you know that solution exists. Right? So what is the solution here?
B is equal to 3.
So 2B is equal to 7. So B is equal to 7 by 2. Right?
Yeah.
So your A is equal to
-1.
3 minus 7 by 2. Okay?
Yeah.
So minus 1 by 2. Okay? Fine?
Yeah.
Yeah.
Okay. So this you can do the same exercise.
We have added the two equations to find the solution.
Sorry?
We have added the two of them now, like 2A in the two equations formations. Then we are finding the A and B now.
Yes.
Okay.
So you can try this as a homework and find the same A and B here. Okay? Fine. So now we will see what are linearly dependent and linearly independent vectors. Okay, so first of all, let us look at the scenario for two vectors. So let us say you have two vectors u and v. Okay, and suppose you know that u is equal to alpha v, then what can you say about u and v?
Linear combination.
Linearly dependent.
Linearly
U and v
dependent.
are linearly dependent. Now suppose you have more than two vectors, then this is the definition. You look at a linear combination. If you are able to have some non-zero scalars such that this kind of a equation is possible, then you know that the given set of vectors are linearly dependent. So clearly here you see that u minus alpha v. So here some alpha is non-zero. So you have that some coefficient 1 and minus alpha are non-zero coefficients. So you know that this equation
Dependent.
is satisfied for non-zero coefficients. Hence, u and v are linearly dependent. Now, for linear independence, you take this kind of an equation. The only possible solution is all the coefficient is zero. So
Also,
then it means that it is linearly independent. Okay. So the following exercise is kind of a summary of the properties we have seen so far. So let us say you have three vectors and these three vectors are linearly dependent. So if they are linearly dependent and you are forming a matrix out of them, what can you say about that matrix? Suppose,
Determinant
Determinant
is
is zero.
equal to 0.
yeah. So for this matrix, you know that the determinant is definitely zero.
zero.
Right? So determinant of A is 0. So if determinant of A is 0, what can you say about Ax is equal to B? It can definitely not have
Unique solution. Not a unique solution.
right. This can definitely, this will never have unique solution. Okay, so either it can have infinitely many solution or no solution. So you see from the following options, which one is correct? The first option, unique solution is a possibility is given, so which is incorrect. And second option is no solution or infinitely many solution. This is correct. This is incorrect. And option 4, definitely incorrect. What about option 5? Is the matrix invertible? No, right?
The determinant is 0.
So the matrix is not invertible. Okay. So if you have three vectors and here you are forming a 3 by 3 matrix from these vectors and you see that the determinant is 0, then the system will first of all have no unique solution and the determinant is and the matrix is not invertible. Okay. So
Determinant is 0. How?
yeah. So everyone look at this question. Think about this for a minute.
Linearly independent, ma'am.
Independent.
Linearly dependent.
Independent.
Ma'am, homogeneous situation. These are homogeneous.
Think
Yeah,
about
yeah.
take 1 minute.
Dependent.
They are dependent or linearly independent?
I think it's dependent.
Independent.
Independent.
Again, I'm saying those who have answered, not answered, everyone take another minute and think.
Ma'am, we can't say anything about this, right? Because it always has the unique. It always has the trivial solution.
Linearly
Independent.
independent.
It depends on the scenario, right? So, okay. So, for example,
Yeah.
so here Ax is equal to 0 has a unique solution. First of all, we know that x is equal to 0 is the only solution, right? So, now what can you say? Suppose, let us say you are having an m by n matrix. Okay. Now, suppose rank of A, suppose you know that it is n. Then what do you know?
It have unique solution.
Yes. So, and that is the only case when you have unique solution, when you have the columns to be, in this case, what do you know about the columns?
Equal to rank.
Linearly independent. So, for x is equal to 0 to have a unique solution, this is the only condition, right? So, whether you have a rectangular case or square case, so this is the only scenario when you have a unique solution. Only when rank of A is equal to n. So, this means what? Your nullity is 0. So if nullity is 0, rank is n. So it means you know that the columns are linearly independent, right? But what about the rows? Can you say anything about the rows? You cannot say, right? So for example, in the square matrix case, or let's just write n by n. So for n by n case, you know that the rows are also linearly independent. But what about m by n case? In the m by n case,
It will be dependent.
yeah. So for example, let us say 1 0 0 1 0 0. Now for this matrix, does it have a unique solution or not?
No.
Unique solution.
It has a unique solution, right?
Yes, it has
Yes, ma'am. Yes.
Rank is 2, so it has a unique solution. Now for this, what is the are the rows linearly dependent or independent? Look
Independent.
Depend.
at the so whenever you have a 0 row here, so you know that the rows are
Independent.
dependent.
Dependent.
0 row means dependent. Okay, so you can definitely say that columns are linearly independent, but rows may or may not be linearly independent. Okay, both are possible. Okay, it may be linearly independent and may be linearly dependent. It depends on the matrix. Okay, fine. Okay.
So the answer is columns is independent and rows may or may not be, na?
Yes, yes. Okay, so what are the ways of checking linear independence? That is what we are going to see. So whenever you take only the 0 vector for R2 or R3, can you say what is the possibility?
Linearly dependent.
Linearly dependent.
Always it is linearly dependent, right? Okay, and if you are taking a non-zero vector,
Linearly independent. For single, yes, not two for linear.
yeah. Now when you
Yes,
have
ma'am.
two vectors u and v, so how do you check linear independence? You see whether one is a scalar multiple of the other for R2. So when one is a scalar multiple of the other, you know that they are
Linearly
they are not multiples, they are
linearly independent.
Linear independent.
okay. So the exact same thing is applicable here as well. Now there is another method to check linear independence for R2 in this scenario. Can anyone tell what is the other method?
Determinant is equal to 0.
Exactly.
The
So you can
determinant is equal to 0, then it's
yeah, you can
independent.
write them as columns and check the determinant. So if determinant is non-zero, then you know that the vectors are linearly
Not independent.
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 And here they are linearly
Dependent.
Dependent.
okay. And for
For
3
all
vectors,
matrices, ma'am, this applied.
yes, like this
If that is
particular
equal to 0,
two vectors from R2, you can apply this method, and you for exactly similar thing is applicable for any square matrix. So for example, if you have 3 vectors and you form a 3 by 3 matrix, then the exact same thing. Determinant is non-zero means linearly independent. Determinant is 0 means linearly dependent. Okay. Now suppose
And for checking the linearly dependent and independent, we have to write the vector in the matrix has a column vector, na?
yeah,
ma'am, one representation of how vectors are computed as matrices, only just a recall.
see for example here if you have 1 comma 2 and 2 comma 4, then you write 1 comma 2 2 4 and then find the determinant of this matrix. The determinant is 0 here, so these vectors are linearly dependent. Okay, now in R2 suppose there are 3 vectors, what can you say?
Linearly independent.
Always
You
linearly
don't have to do any
dependent.
calculation, straight away you can say linearly dependent, right?
Yes.
And what about 3 or more vectors in R2 or R3?
Linearly dependent.
Yeah. So in general, if you have more than n vectors in Rn, then you know that that set is always linearly dependent. Okay, fine. What about any set which contains a 0 vector?
Linearly dependent.
Linearly dependent.
Linearly dependent.
Dependent, right? What about a superset which contains a linearly dependent set?
Linearly dependent.
Linearly dependent.
Dependent.
What about a subset of a linearly independent set?
Linearly independent.
Linearly
Linearly
independent.
independent.
Linearly
Okay.
Independent.
independent. Yes.
Okay. So how can you check linear independence? By solving system of equation. So whatever vectors which are given here, you write them as a matrix. Okay. So you write them as a matrix, and then what you do, you look at the solution of Vx is equal to 0. Okay. So each vector is written as column, and then you solve Vx is equal to 0. If you have only the trivial solution, then your vectors are linearly independent. If you get non-zero solution, then you have the vectors are linearly dependent. Okay, so this is one way to check linear independence. So when you have many vectors, you can use this technique. Okay, obviously for square matrix, you can simply switch to determinant method, right? Okay. Okay. So the next topic here is, what is span of a set? How do you find the span of a set? Span of a set is all possible linear combinations, right? All possible linear combination is called span, right? So for example, here you have two vectors. So how does the span of S look like? So let us give some names, V1, V2. Okay. So if you have V1 and V2, what is span of S?
Alpha 1 V1 alpha 2
Alpha 1 V1 plus
plus alpha 2
alpha 2 V2, where alpha 1 and alpha 2 are real numbers.
real numbers.
Now the question is, you are given a vector, okay, and there is one missing number here. How will you find A so that this vector V is in the span of S? So it is given that minus 1 comma minus 8 comma A belong to span of S. How will you find A?
B equal to
Alpha
alpha
is
V1
of
plus
V1 plus alpha
B
times
is
of
equal to
two minus.
You
B is
have,
equal to alpha V1.
We
yeah,
find
you have
alpha 1 and
tried
alpha 2.
alpha 1 1 minus 1 1 plus alpha 2 1 2 3.
2, 3.
Everyone try this and find A. Find A by creating the system of linear equation. Find, you first have to find alpha 1 first. You have to find alpha 1 alpha 2. Then you have to find A. Everyone try this one.
-7.
What is minus 7?
Value of it.
Value of A. Okay. What about alpha 1?
Value is 2.
Okay. Alpha 2?
And -3.
Okay. How many of you are able to get this answer? Okay. Others, I guess you are still trying the solution.
A is equal to -1.
A is equal to?
-7.
Yeah.
Alpha 1 is 2 and alpha 2 is -.
Are you all able to understand how to find the A here? Is it clear for everyone?
Yes, ma'am.
Okay, good.
Ma'am, can you please help in finding that solution?
See, here you first have to write them as equations. So you have minus 1 is equal to alpha 1 plus alpha 2. And then minus 8 is equal to minus alpha 1 plus 2 alpha 2. So you have a system of linear equation. You first solve it and find alpha 1 and alpha 2. Next, what you know? You know that A is equal to alpha 1 plus 3 alpha 2. Substitute the values you have found from the system of linear equation here, and you find A. That's all. Fine?
Okay, ma'am.
Oh.
What is the answer? What is the value of A?
Equal to -7. Okay, and alpha 1 and alpha 2 are here.
Ma'am, previous slide why determinant is 0.
Sorry, what?
In previous slide why determinant is 0.
Here? This one are you asking?
Yes, ma'am. Can you give me an example?
Here is an example. You know that u v is here. V is equal to alpha u. So you know that the determinant is 0, right? So whenever you have one vector is a scalar multiple of the other, you know that the determinant is 0, right? Because what happens when you apply row elimination, you can make this, or row or column elimination, you can make one of the row or column as completely 0. Then that determinant is 0. So it means the original matrix determinant is also 0, right? Yeah.
Okay, ma'am.
So just a quick question from here. Suppose you have one of the vector as a linear combination of the other two. So for example, here you are having u, v, w. And suppose you know that w is equal to alpha u plus beta v. Then what do you know about the determinant?
0.
Determinant is 0, because obviously you see that u, v and w are linearly dependent, because this is obvious linear combination of u and v, w. So you know that the determinant is 0. Okay. So extending that to span. So suppose you have here v1, v2 and v is there. Suppose you are forming a matrix out of these three. Okay. Can this have a unique solution? Can this have a unique solution? What is the determinant of A? So here, sorry, it's V, not V3. V1, V2 and V.
0.
The determinant is 0. So it means, can this equation have a unique solution?
No.
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 Okay. Fine. So suppose whenever you are having a vector from the span of the other columns or rows, then you know that the matrix will not have a this matrix is non-invertible and the determinant is 0. Right? So the next set is, what is a spanning set? Let V be a vector space and S be a subset of V. Now S is said to be a spanning set if span of S is equal to V. Okay. Now, so for example, I'll give you some examples here. So suppose say I am having.
Ma'am, I just have a small query.
Yes.
Ma'am, so like whenever, like say for example, we are finding the determinant just to determine whether it is linearly independent or not. So the vectors, we basically place it in form of columns, right?
Yes. Okay.
Yes.
For square matrices, it does not matter whether you put it as columns or rows, but for non-square, you have to put it as columns. But to avoid this confusion, I always say put it as columns.
Columns, okay.
Okay, fine. So here you see that this is the vector space I am considering. Okay. Now, what is a spanning set for this? Can you tell which one is a spanning set, S1 or S2? Which one is a spanning set?
S2.
S2.
What about S1?
S1 is basis.
One is the element that contained in this. Normally the basis actually, but then S2 is just a spanning set.
Yeah, S2 is span.
So both both S1 and S2 are spanning,
Yeah, spanning sets.
right? But
Yes,
only S1 is
Basis.
basis. Right? Many of you have made mistakes in, I guess, in quiz 2 or quiz 1 only. This kind of a question was there, right? So which of the following form a spanning set?
Yes, ma'am, I did.
Yeah. So please remember, spanning set need not be a basis. There can be several spanning sets, right? Spanning set need not be even of the same size also. It can be of different sizes. Okay. Now, for example, let me give you another set, maybe from R3. Now try to find.
Spanning set is the set of all linear combination of that vector. No?
No, spanning set is, so for example, here, this is a spanning set. Now, all possible linear combination of this set will give you V. Okay, so here alpha times of 1 comma 1, this is the all possible linear combination. That is your set this. So here you see that alpha times of this and beta times of this is actually nothing but alpha plus beta times of the same vector only, because this you can write as 2 times of again 1 comma 1.
And we can say only V is a spanning set.
No, both are spanning sets, right? Because
V.
see what happens here. What is span of S2? Span of S2 is nothing but alpha times of 1 comma 1 plus beta times of 2 comma 2, which is giving you alpha plus 2 beta, alpha plus 2 beta. So you see that finally you are ending up with the same set. What you finally need is that these two should be the same. That is what you
Yes,
are getting here also.
okay.
Right?
Yes, ma'am.
Yeah.
Got it.
So we have to conclude doing this operation, right? To decide whether it is spanning or not.
Sorry, what?
We can conclude it as a spanning set after doing this scalar multiplication and addition, right?
See, one thing I can tell you. So as long as you know that at least you have the minimal spanning set inside, and whatever extra vectors is there, you don't have to worry about it at all. Okay. So anyway, you know that the span of this is going to be this. Okay. So suppose let us say you have some vector space V, and then you know that V1, V2, okay, V1, V2 are this minimal spanning sets, kind of basis, let us say. This is forming a basis. Now, suppose I am having V3, V4, V5, so many other vectors together with V1, V2, and I know that V3, V4, V5 are all linear combination or scalar multiples of V1 and V2. Then you don't have to check anything. You know that this is also a spanning set. Okay, as long as you know this criteria, then you know that this is also a spanning set. Okay, fine.
Let's conclude with R3.
Yeah. So here R3.
Ma'am,
Yes.
I have one doubt.
Yeah.
L1, 0 and 0, 1 will be the spanning set.
Yes,
of
obviously.
this vector.
For R2, that
of
is
this
a base,
vector space.
any basis is a spanning set. Okay. Fine.
One question. Does the vector of the spanning set need to be from vector space?
Definitely.
Like 1, 0 and 0, 1 is not from the vector space V. But
Okay,
it will be the spanning set, right?
No. For this we, okay. For this we, you are asking, okay, now I understand your question. So you are saying that suppose you have a set S, so 1, 0 and 0, 1, right? So now what is span of S? Span of S is actually R2, right? So spanning set means the span of S should be equal to V, right? So now your V is just a subset of the spanning set. Okay, you understand? Okay, it is not equal to span of S, it is just a subset of spanning set. Okay, fine. So here X comma Y comma Z is
So spanning set is the in the spanning set the basis vectors and the some linear combination of those basis vector is included.
can be included, yes.
And ma'am, in R2, the basis is always 1, 1.
See, it's not R2 we are talking about. We are talking about V. This set. For this set, 1, 1 is a basis. There are infinitely many bases. Okay, I guess we have done enough discussions on this question. Let's move to the next topic. So for R3, I'm giving you a set. Try to find any spanning set for this. So let me write in a different color so that you know it's something different. So here, let's say V is equal to set of all x comma y comma z such that, let us say, x minus y minus z is equal to 0. Find a spanning set for this space. Everyone try this. How do you do this?
Ma'am, we take one variable in terms of other two and create a basis vector initially. Then we can add our wish if to make it spanning set.
So z is equal to, for example, I can take it as x minus y. Okay. So now you know that if I take x, y, x minus y, this is my v. This is my v. Right. So you see that now x minus y minus z is 0. Right. So now you see that one of the spanning set can be 1, 0, 1, 0, 1, minus 1. Right? Now, suppose instead of this, if I want to write it as, let's say, x is equal to y plus z. Okay, I'm taking x is equal to y plus z. Now, I can represent the same v as y plus z, y and z. Right? So, now another spanning set I can form which is completely different from this. So, here I can have, for example, 1, 0, and then 1, 0, 1. Okay?
Ma'am, can you tell how you're taking 1, 0, 1?
Because here you see that y times of 1, 1, 0 plus z times of 1, 0, 1 gives me this. So these are the vectors I'm taking here. I'm just taking out this y and z and I'm finding these vectors. And this is the exact procedure to find the basis actually. Okay. So these S1 and S2 are in fact bases here. Okay. You can add any linear combination here or you can combine S1 and S2. That will also form a spanning set.
Also, again, there can be like infinite bases, like 2, 1, 1 can also be a basis.
Yes, yes. But not one vector. One vector is not sufficient here. You need to have two vectors for a basis. So 2, 1, 1 and you need to have one more element here.
And why do we need 2
independent
here?
vectors.
I'm not getting that. Why we need 2?
Because you have two free variables here. You cannot reduce this further with one variable. You cannot have this vector space represented with only one variable. You need two variables to represent this. So it means you are in need of two vectors to represent the set V. Okay?
Okay.
Oh.
I mean, spanning set, it is necessary to have the bases in it.
Yes, spanning set always contains the basis. Contains a basis.
Okay.
Fine. Is a spanning set of a space unique? Obviously, no.
Yes.
Obviously, no, right? It cannot be unique. You can have infinitely many spanning sets. Okay. So, what is the basis of a vector space? A basis of a vector space V, it satisfies that it is first of all linearly independent and it spans V. Right? So, for example, for this particular V, S1 and S2 are in fact bases. Okay, S1 and S2 both are bases because they are linearly independent and also they span V. So these two are bases. Okay, so maybe a simple question from R2 I will give. Find a basis for it. So let us say you have W is equal to set of all x comma y such that 2x plus 3y is equal to 0. Can you find a basis for this? So you have 2x is equal to minus 3y. So y is equal to 2 minus 2 by 3 times of x. So this is nothing but x comma minus
2 by 3x.
So what can be a basis? 1 comma minus 2. Or you can have 3 comma minus 2. Okay. So any one of this can form a basis for this W. Okay. Now let me give some example from M2 of R. Try to find a basis. So let us say you have okay. So A, B, C, D. Okay. Such that A plus B plus C plus D is equal to 0. Can you find a basis? First of all, is this a subspace? You take any two matrix, you add them up, you already know that the first matrix entry's sum is 0, second matrix entry's sum is 0. So it is closed under addition and obviously closed under scalar multiplication. So it is a subspace, right? Okay, find a basis. How to do that? Exact same procedure. You write the matrix A, B, C, D as A, B, C, and instead of D, put minus A, minus B, minus C. Right? So you can now,
0.
yeah, 1, 0, 0, minus 1 plus 3 times of
0, 1,
0 minus 1.
0 minus 1.
plus C times of 0,
0, 0, 1 minus 1.
1 minus.
Okay. So you see that let's call this A1, A2, A3. So this 3 matrix will form a basis for this vector space. Okay. So
Ma'am,
is
for
it
D it is 0, 0, 0, 0, no?
See here there we don't have D at all here. So you don't have to worry about D. We have already reduced the variable D. So we need
Okay,
not
ma'am.
reduce D.
So these are the only 3 bases for the vector space.
This is one possible set of bases. You can have like this, you can form many other bases as well.
Ma'am, I'm saying the 3 combined make
Yes,
the
combined.
basis for
Yes,
this vector.
yes, yes, yes.
And the dimensions will be 3.
Sorry, what?
The dimensions will be 3
Yes.
and the vector set is
This is your vector space.
Ma'am, can you tell the first sum of the matrix is 0? How it like?
What is your question?
In the starting, ma'am, you told no, right, ma'am? The first matrix sum is 0 and second matrix sum is 0. Like, how did you
Okay,
confirm
how
that?
it is closed under a vector addition you are asking, right?
Yeah,
So let's
yes,
say
ma'am.
you are having two matrices A1, A and B from B. Okay, so you know that. So let us say the entries of A are A1, A2, A3, A4, and the entries of B are B1, B2, B3, B4. Okay, what is that? You know, once they are in B, you know that sum of A1, AIs are 0 and sum of BIs are 0. Right? This you already know from this condition. Now, what is A plus B? A plus B has A1 plus B1, A2 plus B2, A3 plus B3, and A4 plus B4. Now, what is the sum of all elements of this? It is nothing but, so summation A plus B ij is nothing but summation AI plus summation BI. And we know that this is 0, this is 0. So it is 0. Fine?
Yeah, thank you.
Yeah. Okay. So here you have some simple questions. Is every spanning set a basis for V?
No.
No.
Obviously.
Not like
No.
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 Is every linearly independent set a basis for V?
Yes,
No.
ma'am.
Every linear independent.
Yes.
No.
Minimal
So for R3,
Maximum linearly independent set
uh,
forms.
so you see that this is linearly independent or not?
Yes, ma'am. It's a basis also.
Linear independent,
It
but
is a
not a
basis.
basis, right?
No,
Like
Yes.
if it's not basis for R3, ma'am. Like
Yes.
it's not mentioned. R3 should be
Yes,
required, right?
R3 it is
But
not.
it
In
is
V,
not for
basis
R2.
for V, it's mentioned. Okay. So in V, it is not a basis. Okay. And relation between number of elements of linearly independent set, basis and spanning set. So always you know that the number of elements in any linearly independent set is less than or equal to the number of elements in basis is less than or equal to the number of elements in any spanning set. Okay.
Ma'am,
Yeah.
ma'am, would you mind explaining the second one, please? Is every linear independence? Yeah, this one. Yes, ma'am.
Okay. So this set is linearly independent. Can you see
Yes.
that?
Yes. Correct, ma'am.
But for R3, how many elements you need for basis?
3. Okay.
Yeah, you need 3 elements in basis. But how many you are having here?
Oh, got it.
Okay.
Could you repeat the third point?
This one, right?
Yes, ma'am.
Yes. The number of elements in linearly independent set is always less than or equal to number of. So all this is for one particular vector space we are talking. Okay. For any vector space, you take any linearly independent set from V. Okay. And any basis for V and any spanning set for V. Now the number of elements in the linearly independent set is less than or equal to number of elements in basis, and that basis number is less than or equal to number of elements in spanning set. All right. Spanning set can have more elements than basis. Linearly independent set can have less than or same elements as that of basis, like here. Okay. For example, same I can give example in R3. Right. In R3 you can have 1 0 0 0 1 0 as a linearly independent set. And then you can have for basis, you can have 1 0 0 0 1 0 0 0 1 as a basis. And then you can see that maybe you add one more vector. Let's say E1, E2, E3 you are already having. And then let us say you are having another vector. It is a spanning set. Right? Now this is a spanning set and you can compare the same relationship works here. Clear? Yeah. So for any basis, it is linearly independent and it is a spanning set, and it is a maximal linearly independent set and a minimal spanning set. So it means it cannot have more. So any linearly independent set cannot have more than the number of elements in basis, and minimal spanning set in the sense that so any spanning set should have at least this many elements in the basis. Okay. So is this basis is the basis of a space unique?
No.
Obviously
No, ma'am.
no. So suppose let us say you are having u comma v comma w is a basis for R3. Can we say that for some alpha non-zero, alpha u, alpha v, alpha w is a basis?
Yes.
Yes.
So
No.
easily you can see that this way you can form infinitely many bases.
Ma'am,
Okay. Fine.
ma'am,
Yes.
Ma'am, excuse me.
ma'am,
One question.
we can form the spanning set.
This one?
Yes, ma'am, like that S is given 1 comma 1 and 1 comma minus 1, and we need to find the spanning set for that. Then simply we can just alpha times of that.
Which one?
Yes. Ma'am, I'm asking that, for example, in notes sir has told, so I'm asking the question that if S is something given 1 comma 1 and 1 comma minus 1, and we need to find the spanning set for that.
Okay.
Then we need to simply find A and B and then put the value there.
So you are saying you are given V1 as 1, 1 and V2 as 1, minus 1. And
Yes,
you
ma'am.
are asked to find what is span of V1, V2.
Yes, ma'am.
Yeah, so it is nothing but alpha times V1 plus beta times V2, where alpha and beta are varying in R. So what is that you will get? You will get alpha plus beta, alpha minus beta, right?
Yes, ma'am.
Yeah. Suppose if you want this in terms of some x comma y, then you have to solve for it. You have to put alpha plus beta equal to x and alpha minus beta equal to y. You have to express alpha and beta in terms of x and y to solve this, to write this in terms of x and y.
Okay.
Okay.
Ma'am,
Okay.
I want to ask one thing. Is basis for the vector space is unique?
That is what I asked here. So is the basis unique? Answer is no. This is one example I have given here. So both these are basis for
Basis,
nothing.
nahin, ma'am, I am not clarified. Still not. Basis means a smallest space, right? So we cannot say a vector space has only a unique basis or not.
We cannot say that because, for example, this is a basis. This is also a basis. This is also a basis. Like this, I can write infinitely many bases for R2 itself, right? Any two linearly independent vectors from R2 forms a basis for R2, right?
Particular vector space, I am saying.
What is that you're saying?
I'm saying for a particular vector space is basis for that particular vector space
This is the
is
particular vector space I have taken. And for this particular vector space, this is a basis, this is a basis, this is a basis.
okay. That is like a linear dependencies among them, or
Yes.
not?
Yes. So all these form basis for R2.
Ma'am, but
Okay, ma'am.
within a basis, both the vectors have to be linearly independent.
Yes, that is the condition mentioned here, right? They have to be linearly independent and also it should be spanning. So they are linearly independent and they should be spanning. This is one separate set, and for this set, this property should be there. Okay.
Ma'am, can you explain that the below part, ma'am, the which you have written? Not this one, ma'am. The alpha plus beta and alpha minus beta. No, ma'am. You have written. Yeah, that thing.
So alpha times of 1, 1 plus beta times of 1 minus 1. I have just expanded it. What is your question?
Ma'am?
This is nothing but alpha times of 1, 1 plus beta times of 1, minus 1. I have just did the calculation and written here. What is your question? So this is alpha V1 plus beta, right?
Alpha minus beta is not as a vector addition, right, ma'am? So that's the reason. Yeah, now I got it.
Okay. Okay. So suppose you have two bases for V. What do you know about the number of elements in B1 and B2?
Equal.
Equal.
Equal, right? Okay. If S is a subset of R5 such that span of S is equal to R5, what is the minimum number of elements possible in S? Yes.
Minimum number can be 5 or 5.
At least it should have 5, right?
5.
Yes, ma'am.
Okay. Now suppose you are having a basis, or let us say a linearly independent set. Basis means it's very obvious. Suppose let us say you are having, let us say, some set, I don't know what notation shall we use, S only, some S dash. S dash is a linearly independent set in R5. Okay. What is the maximum number of elements possible in S dash?
5.
Again 5, right? So for spanning set, it is the minimum number, and for a linearly independent set, it is the maximum number.
Maximum linear independence set.
And the dimension is exactly the size of the cardinality of basis, right? It is the size of the basis. Okay, that is the dimension.
This is 5.
Yeah, cardinality and size just refers to the number of elements, right? So what is
Maximum
any
dependent sets can be independent, na? Dependent,
maximum?
maximum dependent. Linearly independent sets can be infinite.
It linearly dependent set can have any number, that does not matter, but linearly independent maximum only 5. Okay. Okay, any basis for Rn has how many numbers, number of elements?
N number of elements.
N elements.
N.
So dimension of Rn is n.
N.
Right? Now here you are having a set of vectors. What can be the dimension of the space vector?
2.
V1, V2, V3. What can you observe? V3.
Ma'am, we have to make a matrix out of it and then dimension, right?
Yeah,
V3 is a
almost
linear
matrix is
combination
not
of V1 and
repeated.
V2.
This is a very obvious case, like alpha V1 plus alpha
That
V2.
2, right? Yeah.
So if this is obviously given to you, then you know that, and V1 and V2 are linearly independent. So you can clearly see that the dimension of W is
2.
Okay, the number of linearly independent vectors here. Yeah.
But for R3, basis can't be 2, right, ma'am?
Yeah.
We need to check the dimension for basis only, right, ma'am?
We are looking at W. Okay, we are not looking at R3, we are looking at W. What is the dimension of W?
Ma'am.
Yeah.
Ma'am, the given set is not a linearly independent set.
Yes.
Right. So it can't be a basis.
Yes. But how, that is what is the question here. Suppose you are not given a basis, but you are given a spanning set. How will you find the dimension? In that case, you have to look at the number of linearly independent vectors in the spanning set.
Okay, got it.
Okay, fine.
Yes, ma'am.
Okay, so here is an exercise. Can everyone try this? First of all, what can be the dimension for this? Can anyone guess?
Dimension
3. Dimension can be
2.
2. Okay.
2, ma'am.
Yes, yes. So only you need 2 vectors for basis, right? So 2 matrices. So you have x, y, x plus 2y. Instead of z, I can put x plus 2y, 0, x plus 2y, x, y, 0, 0. So this can be written as x times of 1, 0, 1, 0, 1, 1.
0, 0, 0.
Yes.
0, 0, 0.
That's y times of
0, 1, 2.
0,
2, 0.
0, 1, 2.
yes, ma'am.
0, 2, 0. 1, 0, 0.
So you can say this is A1, this is A2. So A1, A2 forms a basis, and also basis, every basis is a spanning set.
Yes.
Okay. Is it clear?
Yes, ma'am.
And how
So-
x is 1, 0, 1, 0, 1, 1, and 0, 0, and y equals to 0, 1, 2, 0, 2, 0, and 1, 0, 0. How?
See, I have taken x out. So for each position, I'm looking at the coefficient of x. So here the coefficient of x is 1. Here the coefficient of x is 0. No x is there. So 0. Here it is 1. Here again 0. Here 1. Here 1. And here no x at all. So all 0. Same for y. No y, 0. 1y, 1. 2y, 2. Like this you have to do for each entry. Okay?
Got you.
Okay.
Ma'am, but where you have put 1 instead of x plus 2y, then what will happen to 2y there?
That's what I'm saying. First for x part, I have put a 1 here. And for y part, I have put a 2 here. So when I add them up, I get x plus 2y, right?
Okay, got it.
Okay. Okay.
Ma'am, let's continue.
It's done. I have completed the revision, so I have completed almost all the topics. Yes.
Thank you, ma'am.
Can you take one example for finding the basis?
One example for what?
For finding the basis for non-homogeneous system.
Finding a basis for
Yeah,
non-homogeneous equation.
from Ax
In a
equal to B.
solution or basis? What's your question?
A basis.
Basis for non-homogeneous equation does not make sense, because a non-homogeneous equation, the solution is first of all not a subspace.
It will be a fine subspace.
Yes. So what's your
Ma'am,
question?
today I've covered how many weeks?
Week 1 to week 4.
4 weeks.
Okay, ma'am. Ma'am, so for the next weeks, there would be further revision sessions.
Yes, on Sunday we have revision for week 5 to week 8, and then on Monday week 9 to week 11.
Okay, ma'am.
Ma'am, will you please provide this notes?
As usual, yes.
The video will be available on YouTube, right?
Obviously, yes.
Ma'am, can any there be boosting sessions for this?
Further boosting sessions. What do you mean by boosting sessions?
Means anything that can start by 7, because every time 8 to 10. Like if they are the end term, like many difficult questions can come.
See, I have covered everything within this 2 hours, and further there are TA sessions where you can cover more problems instead of just a topic. So what are you expecting? If you have doubts, you can ask me. Yes.
Then any previous year discussion also will happen.
Sorry, what?
Ma'am,
Previous year question papers, any discussion also will happen. No?
When? Yeah, in
I'm
TA
asking.
session, yes. Whatever, like I will be floating a form, Google form soon. So whatever specific doubts you have, you can definitely put it there, so that in the TA session, first all the doubts will be clarified, and then they will do some common problems maybe. Okay.
Ma'am, I want to, please, ma'am, I want to give a suggestion.
Yes.
Only 10 marks are given for the graded sessions. This is the loophole of this whole program. If anything is taken as a 10%, literally this is going to 90% is on the basis of our exams. So like we are crashing down in exams. Why
That is
not
what
we
the
are
subject
conducting
is
30% at least for graded assignments?
because we can see there.
We can always
Monitored.
see the answers of grid assignment.
Monitored. So
Ma'am,
no point of giving more marks. Yeah.
Please monitor for this, ma'am. At least any colleges has 40% for their internals.
They are not online institutions, right? So here we are doing online program. So don't compare it with other regular colleges. Yes. I
right.
guess that's not the session about. Maybe it's, some other discussion, some other forum
Ma'am,
for the discussion. Yes.
on Sunday you will take and Monday.
Oh, don't worry about who is going to take the session. Uh,
Mm.
yeah, Sunday the topics are from week 5 to 8. Okay.
Ma'am, you will
Ma'am,
take
can
it.
you tell the weightage for the end like from which weeks the weightage is more?
As I already mentioned, week 1 to week 8 is approximately 50, and the remaining is approximately 50. Okay.
Thank you, ma'am.
Ma'am, will you please upload these notes, ma'am?
Yes, I will.
Thank you.
Okay, so if there are no questions from the subject, we can wind up.
Thank you, ma'am.
Ma'am, but in
Thank you. Yes.
email they are saying that week 9 to 12 cover more weightage.
Sorry, what?
Ma'am, I checked my email and teacher are saying that week 9 to 12 cover more weightage.
Which week 9 to
12.
yes has 50%.
Okay.
Ma'am,
Now
on the
we
It's not exact, it's approximate. Yeah.
yeah, in linear independent set, after multiplying all vectors with scalars, it can be 0, right?
See, if you are doing with a non-zero scalar and then you are finding the determinant, it is still going to be non-zero only, right? If you are multiplying by non-zero scalar, how can it become 0?
What is the difference between linear independent set and linear dependent set? Because I am getting confused. Linear independent variable is the when there is no.
Hold on 1 minute. Don't confuse dependent and independent variable with linear independent and dependent vectors. That concept is completely different. That linearly dependent and independent variable concept, don't compare it with linearly independent and dependent vectors. That is completely different concept and this is different. Okay?
Okay, but this linear dependent vectors and linearly independent, can you please explain just once that according to the definition?
According to the definition, if you are having any set of vectors, okay, so suppose you are having some set of vectors, okay, so if you are considering this equation, okay, so if all ai's are 0, okay, if this is the only possibility, then it is linearly independent. Okay,
Okay,
if
all scalars should be 0, right?
yes, if some ai can be non-zero, then it is linearly dependent. So equivalently, I can put this as a matrix representation, which is Vx is equal to 0. So here your x is a1, a2, an. Okay, and your v is v1, v2, vn. Okay, so if this Vx is equal to 0 has a unique solution, then it is having, the vectors v1, v2 are linearly independent. If it is having infinitely many solutions, then it is having, the vectors are linearly dependent. So either you can put it in this way, or if you want it in terms of system of linear equation, you can put it in this way. Whichever is convenient, you can follow it. Okay?
Okay, thank you.
Yes.
Ma'am, is tomorrow TA session is based on week 1 to 4?
Yes.
Yeah, okay. Thank you.
Can I ask the question from week 11?
We have a session for week 9 to 11 on Monday. Please discuss it at that time. Okay?
Okay, ma'am.
Okay, then we'll wind up for today's session then.
Ma'am, can you give any suggestions? Like, we are understanding the concept, but we are not able to solve the problems in maths.
Practice as many problems as you can. Then solving problems will be a fun.
Yeah, ma'am. Thank you.
Okay.
How we can join TA sessions?
Just click the link from the calendar.
Thank you, ma'am. Good night.
Thank you.